Hi friends, welcome to lecture 3 of Digital Signal Processing course. In this lecture we will study about the linear time invariant systems, which are also known as the LTI systems. So in this lecture we will study about what are the advantages of an LTI system and what assumptions we make to which will lead to a system as an LTI system. So we will understand about the convolution sum, um, which is which actually characterize a linear LTI system, and then we will also study about the properties of LTI system. So let's proceed. So among the signal processing systems or the discrete time signal processing systems, the two important class of systems are linear and time invariant. So this linear and time invariant will lead to LTI systems. So these two properties in combination lead to a very convenient representation of system. Uh, Make a note or focus on this term combination. So when these two properties are applied in combination, the system can be represented in a very convenient manner. Okay, so as discussed that the linear systems are defined by the equation, the linearity equation, which is discussed in the previous uh, lecture, the lecture 2, where the linearity equation or basically the superposition principle. The superposition principle, which was any function taken over a of x1n plus b of x2n will be equals to a t of x1n plus b t of x2n. If so, the LTI systems should be following this superposition principle. Cool. So, as linearity property in general can be represented by linear combination of delayed impulses. So, uh, if system is following the linearity property, we can represent it as a linear combination of delayed impulses. So we can write it as this summation taken from minus infinity to infinity xk delta n minus k. Okay, so this is, we are representing it by linear combination of delayed impulses. Okay, so a linear system can be completely characterized by its impulse response. Yeah, so if this is the case, then we can say that a linear system can be completely characterized by its impulse response. So what is impulse response? Impulse response is, let's say we have a system, if its input is an impulse function delta n, whatever is the output, let's say hn, this is the impulse response. When the input is an impulse function, whatever is the output, that is the impulse response. Okay, so if a system is following this property, or if we can break our input in as a linear combination of delayed impulses, in that way a linear system can be completely characterized by its impulse response. Okay, so let's assume that h HKN. This is the impulse response when the input is delta n minus k. In other words, let's say we have a linear system. If the input is delta n minus k, let's assume that the output is HKN. Okay. So in this way, for a general input, for an input other than delta n, let's assume that the input is xn, the output is yn. Okay, xn, the output is yn. So how can we write yn here? If we know that the impulse response of this system is HKN. Okay, if the impulse response of a system is HKN, if its input is xn, output is yn, we can write yn as summation over k xk. As we know, then we can write this as linear combination of delayed impulses following linearity property or the superposition principle, summation k xk t of delta n minus k. Cool. And we know this will be equals to HKN. So this will be summation over k xk HKN. Here in the superposition principle that we discussed that t of axn is a into t of xn, where a was some arbitrary constant. So in this equation xk is some arbitrary constant because our running variable is n here, while xk is only depending on the k, not on n. The running variable appears in delta n minus k. That's why the function t is taken over delta n minus k. Okay. So here, if only linearity is imposed, if only we assume that our system is only linear, HKN, we know that it's depending on both n as well as k. Okay, but if we impose time invariance also, okay, so let's take a case where on a system we are imposing linearity as well as time invariance. Okay, so in that case we obtain a more useful result if we are imposing the time invariance. Time invariance. Okay, so as we know that as a result, if a system is time invariant, if for an input delta n, output is hn, then for an input delta n minus k, output will be hn minus k. This is if the system is time invariant. Okay, so our equation was yn if only linearity was there, or let's assume a general case, it was summation k xk t of delta n minus k. Okay, so if we are assuming time invariance also, then we can write this equation as yn equals to summation over k xk, and t of delta n minus k means if the input is delta n minus k, what is the output? It is h n minus k. So what is the usefulness that we are seeing here? It is saying that an LTI system or the linear time invariant system, we say it as LTI system. Okay, linear time invariant system. So a linear time invariant system is completely characterized by a linear time invariant system is completely characterized by Hn. Hn minus k is nothing but its delayed version. Okay, so if only Hn is given to us, we can compute Yn by given an input of Xn. Okay, so if for an LTI system, if for a system we only know Hn, which is the impulse response, if an input Xn is given, we can compute Yn. No other information is needed. So this is actually, this equation is because of assuming that our system is linear and time invariant. So these assumptions or these properties are of great importance in signal processing systems or signal processing applications. So this equation is very useful from signal processing point of view. Okay, cool. Yeah. So now talking of LTI system, those are represented by this equation. Yn equals to summation over k xk hn minus k. So this equation has one more name as convolution or convolution sum. Okay, and in shorter form it can be written as this, where it represents convolution. Now let's understand about the interpretation of the convolution sum. So this that equation, that convolution sum equation, tells us that the input sample at n equals to k, represented, which is represented as xk multiplied by delta n minus k, is transformed by the system to output sequence xk into hn minus k, where the hn is the impulse response of the system for all values of n, and that for each k these sequences are superimposed to form overall output system. So the superimposition is represented by that summation. Okay, so the key to carry out convolution sum is to understand how to form hn minus k. Okay, and yeah, this conversion you can think of. Okay, so let's assume that the impulse response or the hk is given as this particular sequence. Now h of minus k or h of 0 minus k, where this hn minus k, where n is equals to 0, we can see that this is given by this, where this is just the mirror image at across n equals to 0 or k equals to, actually the k equals to 0. And this is just the mirror image. So this sample comes here, this sample goes here, this sample goes at minus 3, sample at minus 3 goes to plus 3, sample at 6 goes to minus 6. So this is just the mirror image across the sample number 0. Now as we have to calculate hn minus k. Okay, so this is just the same image of h minus k. As we have to calculate hn minus k, so we will just give a shift equals to n samples to each sample. Okay, so that means the sample at 0 goes to n, sample at 3 goes to sample number at n plus 3, sample at minus 6 goes to sample position n minus 6, and so on. So whatever is the value of n, we will just put the value of n and calculate the sample position. That's the simple interpretation of convolution sum, or that's how, actually that's not the correct exact interpretation of convolution sum. This is actually the way to figure out or calculate what hn minus k will be. So we will just put this hn minus k into that formula, the convolution sum formula, and we will calculate the output. Yeah, so now let's discuss about the properties of the LTI system. So as an LTI system is defined by convolution sum, so properties are also defined by the properties of the discrete time convolution. So first property is it is commutative. The convolution sum is commutative. That means xn convolution hn will be equal to hn convolution xn, because it follows from the linearity property. Simple. Second, it distributes over addition. Actually, this is also a result of the linearity property, because the system is linear. So xn convolution h1n plus h2n is equals to xn convolution h1n plus xn convolution h2n. So these two are the result of the linearity property, because the system is linear. Next, what happens in a cascade connection? So let's assume that if two LTI systems are connected in cascade. Cascade means one after another. Okay, let's assume the input is xn and the output of the second is yn. So, and we write, and let's assume that this is one system, the cascade connection of two. So yn equals to xn convolution hn. So we can write here as hn is equals to h1n convolution h2n. So how this comes? So let's assume that as an intermediate output, this is y1n. Okay. So here y1n is equals to xn convolution h1n and yn is equals to y1n convolution h2n. Okay. So if you put y1n equals to xn convolution h1n, so in that way yn will equals to xn convolution h1n convolution h2n. In that way hn can be written as h1n convolution h2n. So this will be xn convolution h1n convolution h2n. So this is hn. Okay. Proceeding further, what if two systems are connected in parallel? Yes. So if two systems are connected in parallel like this, h1n h2n, this is the output yn and this is the input xn. So using the same logic here, making it as one system, hn only, xn, hn can be written as h1n plus h2, and so here you can assume that this is y1n, this is y2n. So y1n is equals to xn convolution h1n, y2n is equals to xn convolution h2n, and yn will be the addition of these two. So in that way we can calculate that hn is equals to h1n plus h2n. Yeah, so now comes the property of stability. Yeah, for an LTI system to be stable, uh, it should follow this equation. If the absolute sum of the impulse response is bounded or it's less than infinity, we can say that the system is stable. So this can be shown as follows. We know that yn is equals to summation over k x k h n minus k. So as we talked about that convolution is commutative, so this can also be written as summation k h k x n minus k. Okay, so taking the absolute of both sides, yn absolute of this term, I'm sorry, this is h k x n minus k. Okay, from Cauchy-Schwarz inequality, if we take the individual summations or individual amplitudes mod, this can be written as this. Okay, so here we for stability we are again talking in terms of BO stability or bounded input, bounded output. So if we assume that xn is bounded, so we can say that is mod of xn is less than equals to bx if xn is bounded. Then substituting this in this expression, mod of yn will be less than equals to summation k mod hk bx. Okay, so thus yn is bounded. Yn is bounded. This statement holds only if this summation is some finite number. So this will lead to this equation. Cool, because we have assumed that we have assumed that xn is bounded. That means this will leads to this mod of xn is less than equals to some bx. So that means for yn to be or mod of yn to be less than equals to some by, let's say, this summation should be some finite number. Okay, cool. Now let's talk about the causality. Okay, so the class of causal systems were defined as those systems for which the output yn naught are depending on only those inputs for which n is less than equals to n naught, or for a causal system the output should not depend on the future input. That's the simple statement. So for them, for a system to be causal, its impulse response should be 0, must be 0 when n is less than 0. Okay, so let's show this in such a way, in this way, that we can write yn is equals to summation over k equals to minus infinity to infinity x k h n minus k. Okay, so y should not depend on some future input. That means that k should always be less than equals to n. Correct? Okay. K should always be less than equals to x. That means the argument of h, n minus k, should always be positive. Okay. So this means that the arguments or the values of k for which uh, uh, I mean those values of k which are greater than equal to which are greater than n, h should be 0 for them. Okay, let's understand this in a better way using an example. Okay, so let's assume that a system is such that our equation is holding up in this way. Let's assume one equation, k equals to minus 1 to 0 x k h n minus k. Okay, and let's calculate n at n equals to minus 1. So y minus 1 will be x minus 1 h 0 plus x 0 h minus 1. Okay, so for this particular equation, y minus 1 is depending on x0. So y at n equals to minus 1 is depending on some future input. So for a system to be causal, if we follow this equation, h minus 1 n less than 0, if this is 0, y minus 1 will be equals to x minus 1 into h0. In this way, y minus 1 is not depending on any future input. So this equation leads that the system is causal.